like with multiple
Please don't make me here.
What's
So you
that?
have 10 where you like go not
I feel
10.
like they get
I can't, 10's not allowed.
They're not
10 is not allowed.
but I rarely see.
9's max.
Like the only reason you should do that.
I have you started it.
Cool. You haven't? Oh, okay. All right, it's 9:06, let's get going. All right. Can everybody see this?
Yeah.
Good thing. I didn't want to have to lead you in. Okay, so, yeah, the room sucks. How many people emailed Mike Hurley?
I showed up in person.
Thank you. It's okay, feel free. If you didn't, it's okay. Mike got the message loud and clear. He's like, I'm scrambling. I'm gonna find you another place. Mike rocks. I told several of you, if you ever need allies in the department, there are two people that you need to ally your forces with. One is Mike Hurley and the other is Susan Ridley. Yeah, be nice to both of them. I don't think Mike drinks, but get him tickets to the Nat. No, he's got season tickets to the Nats game. I don't know. Do something nice to him. Bake him cookies. What's that? Everybody likes cookies. Okay. I sent out an email, and I also know that my email has a tendency to find. So if you could take a look at your whatever Mason Live. I don't know.
Iron and Bolt should have sent you everyone an email saying it's been moved to spam.
Oh yeah.
That's why I got this one.
Oh cool. Okay. What's yours?
I deleted it right away.
Oh, I know this guy delete. Yeah, don't delete. Put me in the I'm okay for now. Later after the course, you can delete everything from me. It's okay. But I sent out a note asking people to fill out a form, a Google form. And if you could do it on your phone today or this morning, ideally, because Jake and I got to sort out the teams. We were going to do it before, but I figured one was I was super busy, but second is I got to figure out or who said that they were good at R. I got 1, 2, 3, 4 of you. Only 4.
I think technically I volunteered myself for being.
Did you? Are you good at R? No, sorry. That's okay. I was just looking for hands and I saw one go up. Amanda, do you want to? Sure. Okay. Because if we have 5, that's good. 4 is a little difficult because we have 24 in the class, and that means 6 people on a team, and there's a lot of social loafing that can go on there. So instead, I'd rather have teams of 5 and 4 or 6 teams of 4. Okay. So we'll sort that out. Okay, so the form, can you get it done maybe at the break? You can even do it on your phone. So just release me from quarantine. I am contagious, guaranteed. But release me and read the email. There's a link in it to the form. If somebody is here and has a computer and you can't unleash your quarantine, whatever the hell that is, while you're in the classroom, just borrow someone's computer and submit it. You have to type in your name and your email address, and the reason for that is it can't be anonymous. I need to know who you are so that I can assign you to a group. As soon as Jake and I get all the responses from the people registered in the class, we will assemble the groups. We'll send out an email, hopefully by tomorrow at about 3. Because if it doesn't happen tomorrow at 3, it won't happen until Saturday. Okay? All right, so that's the form and the email and getting out of spam for at least temporarily. Review. So last week, what I did was I went over some basic operations in linear algebra, matrix algebra, and calculus. Okay, these are very basic, but I don't expect you to master them. I just expect you to have kind of a grasp of their relevance. Okay, so that you can see the symbols and not look at it and go, oh, and then skip. Okay? Because if you do that, some of the readings that I've assigned as either optional or even required, you'll be just skipping page after page after page, and that will be very helpful for you. Okay? As I told you, I'm your tour guide, but I'm not going to walk you through everything because it's not possible. Okay? So there's a good amount of reading, and what I did was I went over a review to kind of set you up for success, for being able to read, and for you to be able to have a fairly good grasp of the material moving forward. Okay? Questions, pressing questions, or even passing about the syllabus, about the review, about anything that I've covered to date. Yeah? We're good? Satisfactory on week 1? Yeah? Good. I noticed nobody dropped, so that was a good sign, or maybe a bad sign. I don't know.
I just wanted my question.
Yeah.
The Think Bayesian, Count Bayesian
Yeah.
blog post that's like assigned for this week's reading. Do you mean read the entire blog, like? Or
No,
do you
no,
read
that link.
Oh,
Just
okay,
click
okay.
on that link. No.
Like, there's like a lot of posts.
Yeah, no,
Like,
just that.
Okay.
Yeah, it's simple. It's a simple primer, because I want everybody from Jeffrey to the Count Basie is somewhat redundant, but it's an extension so that it's much easier for you to understand. And I'm actually going to go over
Okay, cool.
the logic, but go into more detail. So several of you have had classes with me before, but those who have not, I want to just give you guys a reminder about the way I go through things. Is that one, repetition is king in learning. You have to get exposed to things multiple ways and multiple times for encoding to take place. And I subscribe to a helix model of learning, okay? When you start, especially in a class like Bayesian, the weird part about Bayesian statistics in a social science, or actually in any science today, is that for the last, I don't know how many years you've been in this type of environment where you're learning and you're having to apply statistics and think about them and read about them. What you've done is read, thought, and communicated in frequentist terms. Now, the weird part about that, these terms are weird. Well, they are weird. They're weird because it's not the way humans think. That's why you have to have class after class after class to finally figure out after, I don't know, 30 years, you'll have this epiphany like, oh, that's what the p-value is. And then you'll still get it wrong. And that's okay. But that's what you've learned. You've encoded that. And there's a lot of encoding that is taking place. Bayesian statistics, what I'm doing is I'm dragging you all the way back to your undergraduate level in frequentist models. That's why we're doing these things. And you're going to look at it and you're going to say, what the hell is he doing? It's because you got to slow everything down and reteach yourself statistics from a subjectivist point of view. Okay? So I plan to keep it slow, and I plan to keep it deliberately slow, not because you guys are slow. It's that you're very fast. You're quick learners. That's why you're here. But what you're having to do is encode new material over old material that is conflicting. Okay? And it is a huge pain in the ass. It is very hard. So it requires you to read, to watch videos, to watch me, to think about what I've said, to go back and reread. Okay? It has taken, well, Jim Thompson and I co-teach this class. We swap whenever we can. And he and I have read the same books over and over and over again, because every time we read them, we come up with new insights and different ways to teach. And I've decided that I need to go back to more basic stuff, okay? So we're gonna start with basic stuff, and we're gonna stay with basic stuff for the most part. And the helix model of learning such that as you learn, you kind of move up this helix, but it takes a hell of a lot of effort to push this little, you've been to the dentist's office where you're waiting and there's like this little bead that sits on this thing, you know, and you're waiting for so long that you finally walk over there and you start playing with the bead. Because of course you don't want that root canal anyway. So you push this bead up, but that's a lot like learning. It takes a tremendous amount of effort to go very, very little distance in the upward direction of knowing. of knowledge gains. So you have to go very far to get very little. All I can say is my little review is a nudge in the right direction, okay? If you didn't quite get much of what I said, it's okay. It's just one instance of what you could see me talking about in terms of the language or the symbols that are used in the readings. But you can also go to resources such as Khan Academy. I highly recommend the Khan Academy because it's short. You can look at them on your phone. If you're driving, don't watch them, okay? But if you do, actually, we have a bunch of people that probably want to study you. So maybe do that. So avail yourself of all of these resources. Try to expose yourself to as many instances of the material that I'm talking about, okay? It's the best way to learn. As I told you before, I'm your tour guide. I'm giving you all of these resources. I'm going to step you through this stuff. Okay, it's easy to forget. Okay. By now, you should have a pretty good understanding about simple things like probability, okay? And when probabilities are multiplicative. When are they multiplicative? Don't worry, this is not a test. When are probabilities multiplicative?
When they're independent.
When they're independent. Independent events are multiplicative, okay? Classic argument comes from gamblers. Gamblers are fun people. So I was in Vegas. I'm going to give you stories to make this stuff sticky. I was in Vegas one time. My brother was in Vegas. And I was going to the airport. And I was alone. And I was looking over and I'm standing in the United checkout or check-in. And there's this person barefoot. Probably had teeth, but it wasn't apparent. And walked up to the counter and slapped his ticket down and said, I need to sell my ticket back. I'm this close to winning it all. And I thought, man, if I could take a picture of that, that would be awesome. That was the ultimate in the gambler's fallacy. That somehow or another she was owed because she had such bad luck running all the way up there, and she deemed that there was a dependence between every act of gambling. Okay, I'm not a gambler. I don't do that stuff. I spend my money on booze and trips. But some of you may be. And this is one of the lessons you really, really, really need to know. In order for these probabilities to start winnowing down quickly, they have to be independent. Typical gambler's fallacy is the coin toss. You toss a coin, it comes up heads. Okay? You toss the coin again, it comes up heads. You toss the coin again, it comes up heads. And you say to yourself, it's got to be tails the next time. No, it doesn't. There's only a 0.5 probability that it's going to be tails the next time. Not because the next event is independent. Now, what does it mean that these two events must be independent for probabilities to be multiplicative? It's because we're saying and, okay? And this is the reason, this dot, I'll just replace with an X, it's easier to see, okay? And this is something that everybody needs to understand. If you've taken basic, whatever, 611, 612 with me or regression, you'll know that I replace the pluses and the multiplication signs with their logic equivalents. Okay, so this is the logical equivalent of an and statement. And that is the logical equivalent, sorry, Shane. Yeah. And this is a logical equivalent of an or statement. And you've seen this before. You just may not have known this, but look at this statement. Y equals x1 plus x2 plus x1. Right? The hell am I using? Right? So it's just a regression. You've seen this before. Y, the dependent variable, right? We've already talked about this, that this is data. This is data too, from a Bayesian perspective. This is just the outcome that you're interested in. These are explanatory variables from regression. We say this is the dependent variable and these are predictors, slightly different language. We say that this is what we're trying to predict with x1 or x2 or x1 and x2. So what does it mean that these things are multiplied? Well, if I say, what is the probability that I would get 2 heads? That's a head and a head. That makes sense, okay? Because they're independent. Under what circumstances would events be dependent or non-independent, more technically?
Choosing coins out of a jar without replacement.
Yes, okay, yep. The typical, marbles in an urn, right? Yeah. How about we're going to Vegas? None of us have ever heard of marbles in an urn. We've learned about it, statistics, but we've never seen that game. What is a game in Las Vegas that you could immediately think of is definitely non-independent events? Blackjack. Any card game where the decks are not infinite, right? Key. How does Vegas keep you on edge? They keep adding decks, right? It's really freaking annoying. So when you don't have independent events, multiplication of probabilities is not accurate. Okay, we're going to come back to that many, many times. Okay. What's a probability space? Again, for those of you who know me, don't think this is a quiz. I don't give a shit if they please read, but this is not a quiz. I want you to be engaged and to think about this and to be wrong. So if you have the foggiest idea, go ahead and yell out an answer, okay? Best to be wrong, not because it's, yes, it makes you feel uncool and all of that, but you will be super cool in my classroom if you're wrong, because it gives me an opportunity, a teaching moment. Yeah, and I know you guys are all looking around like, I'm never gonna be wrong around these people. Okay. What's a probability space?
Same thing as the density function.
Okay, what's a density function? Excellent, I like that.
It's an estimate of the probability rather than a actual number.
Okay, so, yeah, okay, so the way you're interpreting it is it's the area under the curve, right? It's that space, right? Okay, excellent. Wrong, but excellent. But what he's talking about, though, is good approximation to the way we envision this probability space in terms of numbers. Okay, so that's good because we're going to be talking about the probability space from these density functions. So it's the density function isn't the probability space. The density function is a representation of the probability space. Okay, so now we got to go back to what the hell is the probability space? Yeah.
Is it what you condition on?
Well, it's No, because the probability space is sums to a singular number, always. Well, until it's not normalized, and then it's normalized again, and then it sums to a single number. And what is that number?
1.
Yeah, good, okay.
So is it all possible outcomes?
Yes. Yes,
And
and
you guys' answers first.
yeah, no, this is good because, hey, all right, segue. There's a lot of segues, don't worry, you hear a lot of these crazy ass stories. In the 40s, my rat people or mice people, rodent people will like this. In the 40s, there was a great study that was published about learning. What they wanted to know was how to teach rats much quicker methods for maze navigation. And they thought, man, this would be great. We got this expert rat that can just fly through the maze. And the expert rat would get in there and he could just, or she, I don't know. Would it be he or she?
Probably then.
A he, yeah.
I don't think you want to assume.
Hmm?
I don't think you want to assume.
Okay, it. Is it appropriate for a rodent? Whatever. The rat took off, and all the novice rats are like, "Where'd he go? I don't know." Okay, let's figure out where to go. And they just kind of milled around. Whereas a novice rat who had just kind of sort of made his way and found success walked over to the other rats and go, "Hey, dudes, this way." And he slowly walked them over there without running right toward the whatever food pellet or something that they gave these poor bastards. The moral of the story here is that experts make poorer teachers than novices. Novices are excellent teachers because it's through the errors that we make. And the errors as we go through this, that's why I want you to make mistakes. I don't want you to, I'm not gonna hold you in contempt or raise you up and, I'm gonna say, okay, Shane was bold, excellent, and he provided enough information for everybody to start thinking about it. He gave me a platform in which I could explain things. And then based upon that, then Sam chimed in and gave a little bit more until Amanda could fill in the rest, okay? That's the way these things work much better because you'll encode this better. I was able to explain a little bit of the density function and how it represents the probability space, that the probability space sums to 1, right? And that there's this thing called normalization. And then it's about all the possible events, outcomes, if you will, but they're events, okay? It's a total possible number of events, like here, okay? Can everybody see this? Okay. This is a generic problem, which we're interested to find out whether, let's say, a disease detection mechanism functions well, okay? And we're going to use this example, and I'm going to show you multiple ways in which you can start thinking about these types of examples, but give you a much more fluid way of calculating things to where you're going to be able to beat Bayesian calculators in your heads because it is so simple, okay? This is what's called frequency diagram, okay? Today, I'm going to talk about Bayes' theorem by frequency diagram, by a formula. I'll give you the formula. I generally don't like giving you formulas right away because you look at it and you're like, what the hell is that? And then it just becomes this regurgitation thing. You write down the formula and you think that you know it. But what I'm going to do is I'm going to teach you backwards. I'm going to show you the probability and show you simple things that you can count. And I'm going to count with you just to make sure that my art history didn't screw things up and my lack of counting ability. All my swimming mates know I cannot count. But I cannot count. So this frequency diagram helps us envision what it means to be probabilistic, okay? There's a quick sidebar here. All point predictions today. I thought I might be able to get to updating But I wanna take my time. Okay? Today I want, because this entire class is one that is, relies heavily on scaffolding, okay? If you don't get the stuff last week, this week you'll actually be okay. Eating for the following weeks will be totally an utter shit. Like it'll be a bloodbath. So last week is really important to kind of nudge you up, okay? This week, the Jeffrey stuff is essential. Now notice I had you read it for last week. I need you to read it for last week so you can think about it, think about what I was talking about, and then revisit it with this. This week, I'm going to go through Bayes' theorem step by step in 3 different methods, okay? Frequency diagram, formulaically, and then by odds multiplication, okay? When you reach this point, by odds multiplication, you will be a Bayesian calculator. This method is wicked hack. Only because it's hard to envision these things. I don't know about you, I just don't envision dots or smiley faces or anything like that. But I can reason through a word problem pretty easily by odds multiplication. Okay, so what I'm going to do is I'm going to show you these 3 things with a very simple problem. Okay? That simple problem is going to generalize across all 3 of these methods. Again, when you're done, you won't have any clue about why matrix algebra or calculus are relevant, because at the end of this, I'm going to say, we will then talk about how this can generalize into multiple instances, okay? You can generalize this into multiple events so that the probability space increases. Right now, the probability space is quite finite. You can get point predictions, single digits. Remember the distinction between this and that. Scalar, right? What would that produce?
Distribution. Distribution.
Yeah, a distribution, but if this is a scalar, what would this be?
Vector.
Vector, yes. Remember my notation? I hope some of you find that helpful. If not, it's okay. But I find this very useful. Okay, so today we're just going to talk about one single value that can be achieved by looking at things this way. The transition that we're going to take over the next 3 weeks is going to be implementing Bayes' theorem at the point level, which you will not have in your group project. You will have to convert the point prediction or the logic in this to carry through to producing, rather than a scalar, a vector. And that's when Bayesian statistics really starts. But to get a feel for what we're doing, start at baby steps, a single value. Okay. Let me read you this. You wouldn't be able to read it. And if I read it, you can write it down. Okay. So your job is to screen a set of patients for a disease. Okay, that's your job. What disease it is, we're going to call it this is a class like Prince, except Prince wasn't Prince for a time. He was the yes, he was the artist formerly known as Prince, and he went by some symbol. So we're not even going to use words for this disease. I'm just going to point to this, or worse. Now, you don't need to screen for death. We know that. But we want to imply that whatever we're screening for is important to get, because if we don't get it, well, we get this. Okay. So that's your job, to screen. And we have some data, okay? Based on prior studies, 20% of the patients have the disease. Okay, make sense? In turn, what proportion would not? 80%, right, why? As Sam mentioned before, sampling space provides us a P, right? As Shane pointed out, in the distribution, right, in the density function, the area under the density function is 1, okay? The law of total probability suggests that there's only 2 states that people can be in. They can be in P, happy, healthy, and they can be in P, about to be dead. Okay? Now, because we've set this at 0.2, based on prior studies, let's say, right? This is our estimation based upon prior studies. We'll give terms to these things shortly, okay? But based upon prior studies, we say the probability, expected probability, this is 0.2. So therefore, this is going to be the complement, okay? Because we know that this is equal to, I should never have started with little things. Sorry to turn my back on you. This probability space, the sampling space, you can either be in this state or you can be in this state. You can't be in both, and there's no other state, okay? These are important things, okay? I know that for some of you, you're looking at it going, Jesus, bear with me. The law of total probability is important because as you start seeing these events, you're going to come up with, hey, wait a second, we just lost a few events. And that's what I'll talk about normalizing. So this red thing is the bad side, okay? These are the guys who have this. And these are the guys or gals who are happy. Okay? They don't have that. So therefore, this is 0.8. Okay? Everyone follow me so far? And yes, I'm going slow. I intend deliberately to do this. Okay? So at this point, we've got the proportion of reds and blues. Right? Why the boxes? Well, with everything we do, we have a certain of efficiency, let's call it. And efficiency actually is a term in this, but we'll get to that later. There's a certain efficiency with our screening process. That's what we wish to do, is to detect this, but we use a tool, right? Remember, we use the interocular test. You look at somebody and you say, huh? Think what he's saying. You know, like your mom would do to you. She'd look at you and say, you don't look so good. Here, let me put. Okay. So you're testing for the presence of this disease using whatever test you have. Among the patients who are this way, 90% have a positive test outcome, okay? Right? So that's a positive test outcome. Now, why the other box? No.
They also have positive.
What's that?
False positives.
Yes. So this is a positive positive. These are true positives. And these are
False.
false positives. Okay, now how do we know the rate? 30% of the folks without this, in other words, these people, 30% of them will test positive. Okay, so this too is a positive test outcome. Okay, now let's put some signal detection terms into this. Okay, this helps some people if you know about this stuff. Okay, this a true positive or a hit. Okay, this
False alarm.
or false alarm. Hit, false alarm. True positive, false positive. Okay? The mixture of these terms occurs in the literature. It occurs in informal and formal talks, in books, in instructions. All of this stuff means the same thing. Okay? All right. There's a positive test outcome, there's a positive test outcome. But there's a positive test outcome for people who have it, and there's also a positive test outcome for those people who don't have it. Okay, let us count the numbers.
Example testing.
Oh, hold up. This test. Suppose it's really cheap. Still sucks. Okay, so we said 0.9, right? Is this probability. Now I'm gonna fill in what this probability is and how to denote this probability later when we get to this. Okay? And this probability right? So I'm just trying to fill out all the probabilities, the entire problem so that you can see it. And we're going to leave all of this here. Is where we're going to do this one. We're doing the frequency diagram here, but we're going to do all the calculations in there. Okay. Everyone good there? Okay, now let's count. Okay, shall we? What we want to know is, well, okay, the way I set this up is there are 100 dots. Okay, there should be. If there aren't, sorry. If 20% are red, then there are 20 dots here, right? Rather than count these damn things, so as I said, I failed Sesame Street, there should be 18 of these red dots, right? Okay, so the N here there's N of 18. There's an N of equal to 2, right? Okay. Now, here, there's 80, right? This whole thing is 80, right? So all of the blue dots, there's 80 of them, but only, let's see, 3/10 of them should be in this box. So therefore, there should be
24. 24.
3 times 8.
yes, 24. 0.3 times 80, right? Because all we're doing is, so here, there's 1, 2, 3, 4, 5, 6, 7, 8, 3, right? Okay, we good there? So therefore, this number here is 56. Okay? 56 plus 24 is 8. Everyone good there? We're just getting counts. And this is the reason why this is called a frequency diagram, because all we're doing is dealing with frequencies.
Is throwing me off the capital N.
Yeah, sorry.
Okay, so
Okay.
like the smaller version should be lowercase, right?
I always use capital.
Okay,
Yeah.
I didn't know. I was.
Nah, I'm an atypical, anything I count, I put N, capital N, equals.
Okay.
But subgroups, yeah, easier to follow. Okay, so is we have 20 and 80, we have 100 in total, we have 20 and 80, and from our sampling space, what we're really interested in is the efficiency. How good is this test? Right, Amanda has already led this. So we have to have a question in order to use these numbers. Is given only this information that we have here, a patient comes in to see you. One patient. And they give you a positive. Okay? So whatever test, your interocular test, you draw blood, I don't know what you do, but each of you has a different test. And you have one instance, and you have one prediction. But this is the antecedent, not the outcome. So what we want to know is from this, what is the, I don't have enough space to draw my little character. What is the probability that they fit into this group, okay? This group, given the test. Okay? That makes sense? This is the way we write this. Okay? I'm using funny characters so that you can actually be able to recreate it quickly. Because you'll know very soon that what I'm going to do is I'm going to change things. And I'm going to change things such that this statement will no longer read these funny characters. What I'm going to do is I'm going to say the probability of y given x. Okay? Because this is an observable thing. This is a variable or a characteristic that we're using to be able to predict. And soon you'll know the difference between, and this would be why if I'm trying to explain this, well, really what I'm going to be doing is that. Okay? Because it's a new patient that's come in the door. I've never observed anything about that patient, and I have this piece of data, piece of evidence. Okay, but for now, I'm using this because I want you to be able to generalize from this to the nomenclature that I have. Okay. Now, what I want to know about, and I'm going to use shapes for this because it's the shapes that tell us about these probability statements, okay? What I want to know is I want to know something about the groups in the boxes, okay? I don't care about the patients that are not in the boxes.
They show a negative result. So it's not what we're looking at.
Exactly, exactly,
And are they not in your probability space?
exactly. They're not, because, okay? So what we call this is a conditional probability. I'm changing the space by which I wish to figure out the outcome, a singular outcome. This probability then reverts to two rectangles. Okay? Make sense? So we're going to be using you didn't think I was gonna do $800. And I'm sure as hell not gonna do 24 of these blue things. But just so that you can have it in your notes, and you probably don't have fancy colors or anything like that, but that's okay. But just so that you can see that it's a representation of that to here, okay? We want to know about this. We want to know the relative probability. This to this, right? That makes sense? What was our n here? 18. What was our n here?
24.
24. What's our sample space? 42.
Is sample space the same thing as probability space?
It turns out, well, remember, as I said, later, no. In this case,
Yes.
yes.
Okay.
But our sample space changes, right? Because we got rid of all the dots that weren't in boxes. So now we're here. So we want to know this part. This is the part that we care about. We want to know whether the person has this ugly disease that they're going to die from. And we only want to condition it on the people who actually tested positive. So it's this and this. So it turns out that the way we calculate this, in obviously geometric symbols, I'll give you colors. How about that?
But more consistent or additive on the bottom.
They're frequency counts.
Okay.
Yep, good question. Right? See, you're not fortunate enough to have colors.
Hey, I've got two.
Okay,
Black and blue.
does that make sense? So we have what we're interested in over the total sample space, soon to be labeled as the probability space. Make sense? Okay. What was that n?
18.
What's this n?
42.
42. Roughly.
42.
Is it? You checked?
Yes.
Okay, so the way we calculate this conditional probability is we change the sampling space, right? Soon to be the probability space. And we look at what is the probability that we would observe versus with and without, because that's the law of total probability. We need to have our sampling space, okay? So by doing this, we get a relative proportion of those with and with and without.
Given a positive test.
Exactly, that's why yeah. So Kevin, that's why we carved these out and we laid to waste all of those people who had negative tests. So when we're doing these conditional probabilities, we are focused on only the group that we're conditioning upon. So we are changing our sampling space. By changing our sampling space, we're actually changing the problem. The curveball of this is that when people learn these types of conditional probabilities, the first thing they pay attention to is all of this stuff. They're like, whoa, what about all this stuff that we carved away? And I struggled with this when I first learned probability. I'm like, why are we just discarding all of these things that are part of the original sample that we're discussing? And the reason for it is because we are focusing conditionally. If we had unconditional probabilities, we would have numbers like this, right? Because this is just P of unhappy face with X's. Okay. Yeah.
So that test based on the probability you got is essentially useless because given a positive test, you almost have a 50-50 shot of actually having been signaled. Right?
Well, less.
Slightly less. But
Yes.
if I were the one with disease, I'd be a little sad.
Yeah, well, again, I would hope that you don't pay much money for it.
Did you say you'd be better off not doing tests?
Yes, because the base rate would outperform the test.
Yeah.
How so? Yep.
But it depends also on like what the treatment disease would be. So if the treatment is very simple.
Yeah.
It's very cheap and doesn't cause any side effects. Would it be better to have a test like this where it doesn't matter if you're giving out treatment for people with a false positive?
Yep.
Versus if it's highly invasive treatment. then-
Absolutely. So I want to follow up on that. And I want to follow up, okay? Because this is the heart and soul of Bayesian inference. And this is just a teaching opportunity. There's going to be lots of little tiny things like this inserted in. Okay, this course is about subjectivist views in inference. Subjectivist views, not frequentist views, okay? Subjectivist, okay? So all of you have chimed in saying this test sucks, this, that, and the other thing. You know, we have, those are evaluative statements based upon this conditional probability. But what we really want to know is how do we evaluate this in a logical way that then you can convince other people that something has changed, okay? This is the difficult part, this is the curveball in statistics, is we don't do statistics for ourselves, we do statistics so we can convince other people of our uncertainty of the problem. Maximal uncertainty from anything is usually considered to be 0.5, coin toss. If it's truly, if you're truly uncertain, you can toss a coin, you have no idea, an unbiased coin. Okay? You toss a coin, it comes up heads or tails. You have no idea which way it's going to land. This is the ultimate in uncertainty, right? Okay, so let's represent that on a line. 0 to 1. This, by the way, is your introduction to the beta. Ultimate uncertainty, 0.5. So if I told you I'm really uncertain, you would expect a density function that we'll get to be really peaked here and probably have nothing down here. I'll draw that for you. Beta distributions look like normal distributions, but they're much simpler. We like beta distributions, and we're going to do a lot with beta distributions. This is the point of ultimate uncertainty, okay? It is a state that we call equipoise. It is the point at which you have maximal uncertainty about an outcome. Okay, so suppose we started out, and I'm not going to use distributions here, I'm just going to use, my nice little drawings here. I'm going to use just lines, okay? We started out, hold on a second, that would be 2.5. Because we're only dealing with that side anyway. We started out here. Okay? So we just did, we started out here because we just collected studies. Meta-analysts argue that once you get a probability estimate for an effect size from a meta-analysis, right, a collection of all of the literature that pertains to that question, that becomes an excellent guess. And they're right, to a degree. And in many ways, meta-analysts are Bayesians at heart. So from the meta-analysis, we get a prior probability of 0.2. That's also called the base rate, okay? So we would say that the base rate for this disease is 0.2. So without anything, unconditional probabilities, without anything, my best guess would be that there's a 1 in 5 chance that you've got this. Cost-free. I don't have to go into the doctor's office. I don't have to take the test. I don't have to do anything. I just have to say to myself, what's the probability that I have this? 0.2. Okay, 1 in 5 my odds. Or 1 in 4 are my odds. My probability is 1 in 5. My probability is 0.2. So here on the probability space, we land. Then we introduce this test. You get this test and you now test positive. I calculate through my handy dandy weird ass set of shapes that I stick on top of one another, divide, and I get 0.43. They're the same height, don't worry, because they're just, I'm going to use them as single instances. So we just moved from our priors to our posterior probability of 0.43. I'm writing this out because I want you to write it out yourself. 0 and 1 are our defining points of maximum certainty. Put another way, since we generally don't talk about certainty, we talk about uncertainty, that 0 and 1 are the absolute minimum points of uncertainty. So the minimum for uncertainty and the maximum for certainty. I also mentioned before that this is the point of maximum uncertainty. So I just did this test. And I moved from being relatively close to the ends to closer to the middle. I moved in this direction. That's not so good. Especially if I have to pay money for this damn thing. If I have to pay money for it, then we get people who might say, well, if the treatment is inexpensive, has no adverse events, why not give it, right? Because if the person doesn't have the disease, there won't be any problem. If the person does have the disease, they'll be cured, right? Then don't give the test, give everybody the treatment, right? Because what we want is we want to eliminate costs, right? Think about it in terms of efficiency, yeah.
In those situations where like the cost isn't necessarily financial, like with HIV, they have those
Yeah.
swab ones and they're super cheap, but they do false positives.
Yes,
So
Yeah.
in that case, they just send them for a more thorough test
yes.
for a screening. That's pretty good.
Yeah, and we're going to talk about that when we start talking about repeated observations, okay? The cool thing about Bayes' theorem is that we've done all of this with just one situation, right? But we can expand it, okay? We can expand it to all sorts of things, okay? So let me show you. Just okay. We can expand it to include all sorts of conditional statements so that we still are looking, or we keep our eye on the prize, okay? We keep our eye on the prize, which is the outcome that somebody has this disease. But what we're doing is we're putting in all of these conditions that continue to winnow down the probability space, okay? Yeah.
So when you put all the conditionals in the denominator, is that normalizing? You said before.
Yeah, well, by doing a ratio like this, you actually, it's forced into normalize. Because this turns out to be, when you get, this is a ratio, right? And with this, as long as it stays in ratio form, when it moves into log form, which I'll, or not log form, odds ratio form, that you have to normalize it from the odds ratio. So this, yes, it's normalized by default. Okay, everybody follow me so far there? All right, we're gonna take a quick break, then we'll come back. I'm gonna erase all of this, and I'm gonna show you how this works out in the formula. Bear with me. The formula is so sexy and exciting, it's ridiculous.
Did you see the link?
How did you get?
Still yeah. Layla apparently deleted mysteries. You have that email too.
What did you do?
He accidentally deleted mysteries on the entire calendar.
They were just a little bit.
The mysteries meeting.
Is that what Dan's email was?
Yeah, I just opened it. I'm like, what the? He's hiding it. I think he's sad because he can't come anymore.
Yeah, right, because none of us can have fun.
None for yours.
He's never been interested. That's terrible. I shouldn't be laughing at him. Laughing with him. Hey, thanks for sending out the data list.
I had the undergraduate neuroscience coordinator send that to me. So.
Fantastic. Ooh. But they can't drink, can they? That's okay. They can
Not my
attend.
problem.
Yeah, exactly.
When does that take place? Towards the end of October.
Yes.
October 20-something.
I don't know. It's in my calendar. Disease.
I think it's Friday.
My calendar is like a blur.
Yeah, it says my inbox right now.
You don't have a zero inbox?
No, I used to.
I know.
Start of the semester, I did. I had they had this little thing with clouds and a sunshine when you like clear off all your emails.
The final digit in my inbox might be 0.
I just have to read
The ones columns just for.
You have 3 messages in your inbox?
digits.
You just have 3 digits.
Oh, I have 3 digits. Sure.
Unread.
Yeah.
You guys are impossible. I don't like the notification. I don't like the red.
Well, yeah, but now it's far too late.
So I clear it. I read everything or delete everything. It's just like I can't stand it.
All my unread messages. I usually move it to a different mailbox.
All the calendars.
Is that the
It's
same
like
thing?
cool
I
with the
can't have
calendar.
those little like dots?
We got Yeah.
Like,
I can't have anything like
even
that.
one new email, like I will delete my spam just to get rid of that number.
Facebook.
It's like 1 in the morning.
I wouldn't even, how do you find out in the inbox? Like, the Google inbox, how many messages you got?
I guess it just doesn't say.
It doesn't say. I stopped using the Gmail.
Once
the-
you,
If
once
you
you
go to your
clear the.
preferences and do unread first in your inbox, I think you can right click on it.
I run my household with German efficiency.
I saw that too, I was like, oh,
I don't run my household at all, Patrick.
Sam, we all know that.
I'm along for the ride.
Oh, that's okay.
Well. Or the chat.
Yeah, on this screen, I can't see it anyway, so. Okay.
How was the whip anyway?
She's doing great. She's sleeping in and not having to eat work.
She's doing well, Sam. That one name.
I didn't know she's also not doing great.
Maybe she's
Great
out there
things.
saving
Yeah,
lives.
you should be, you should have
She is
it
doing
now.
well.
It's
Yeah.
what's it?
She's
An
doing
adjective?
good and well.
So it's a substantive adjective.
I'm thinking
The things is implied.
I'm thinking bullshitting right now.
No, that's a thing.
She's doing good, like, wait, was she Mother Teresa or something, you know, like.
No, she's not running a hospital.
Mother Teresa can retire now, she was canonized. She's like, I'm done. Alright, I did everything.
She's kind of past the retirement point.
Yeah.
Some of those miracles were iffy.
A little bit.
Almost.
Yeah, all miracles.
And then you started.
You're gonna, no, Nick, you're gonna learn the tools so that you can calculate the probability of any of those.
Yeah, you can use the loading. Yeah, just coming down. Yeah, you can.
Yeah, that's why. Oh! Burn, Sam!
Find you in this round. I'll come to you with my Bayesian question.
It just takes so long, I mean, like, people but each one 3 hours.
Patrick, that was a game on Sunday, Texas game. Shane, to make a long story short, I don't watch sports anymore.
Oh, you don't? Okay, I thought you still followed NBA football.
Not really. You know what I found is that it wasn't a whole lot of fun anymore, and so I just,
That's fair.
I'm just not into it. I have a whole shit ton of stuff that I gotta do this semester anyway, so it's a good year for me to take off. And I was too invested for it, and I don't think about those anything.
Yeah, and then you get let down and it's just.
Yeah, and my family started hating me. They were like, "Get the fuck out of here, you're nuts."
Yeah, I have a lot of people, a lot of friends that go to UT, they find nuts. Same with Texas A&M though.
I mean, if I can.
Everybody went crazy this weekend. Texas football did well.
Like, over the next 2 weeks, I can actually.
A&M played UCLA, beat UCLA. Texas beat the other day. Like, only 2 teams didn't win in all of Texas, and they lost to Texas team.
We just want to know.
Oh, yeah.
Oh, you worry too much.
Yeah, it's talking about.
What's in here, like, after the wheel? No, like, what's your, you know, like, when you like,
Hey, Spencer, do you know when you control? What's?
I'm going to.
I'm not.
Yeah. Yeah, she's still
Oh, I she hasn't mentally lost it yet.
Yeah, well, she.
Yeah.
She's old. Just when you see the program coordinator, I don't know if you guys know.
Well, we gotta keep you guessing.
You have a straight You send this thing at 3 a.m.
Oh, no. No, I can slip in now. I can slip in until 5. So my son had to be driven to some practice.
Well, she's gonna.
Now,
Bite yourself.
yeah, it's a little dicey. I would love it. He swims up an open water from our house.
Yeah, no,
It's a 12 minute drive. 4 a.m.
Bite
That's why I have a
That's why I'm.
nasty spinach now.
Yesterday I was biking and the number of people I work with moved down. Getting to Kansas, just means I'm used to biking in one place where you say on your left and people move.
Oh, yeah.
Versus here, where you say on your left and they jump to their left in front of you. You're like, no.
Yeah.
I can change one thing. Like seriously, in time.
And then they look at me and I'm like, I did everything I could.
I would do that. When Laura and I started doing this.
Yeah. Sometimes.
It's a year.
Yeah.
Oh my God. They're fake mistake.
Our insurance is really such
No, no,
Sorry.
I'm gonna order coffee. Walk across the ground and go back to sun.
I was like, seven.
She used to have to try to house every Thursday. The software subsite. Yeah, they start off changing
That's honestly why.
It has all the.
Oh, no.
It's like zeros now.
Oh, okay.
This is part of why we see the difference. Now, it's on the other side. Now, we don't have the undergrad focus and then we go all back.
Just don't, just stay on. It's crazy.
Also, I started building
Yeah, if you have like a fragile on purpose, you can just cancel it. Or if you order something and it's not as advertised, so we're gonna skip
All right, we gained everybody? Cool. All right, sorry for the delay.
We're very.
I should never, ever enter my email. Bad idea.
Yeah, they have heard that.
Now I gotta figure out where the hell I left off. What's that?
We moved to one more.
Yeah, no, I'm gonna do the probability. I have,
Jake, what flavor is that bar? What flavor?
Yes.
Yeah.
They're coconut, coca, which
What's
ones are
the
the quickest
probability?
though?
I smell them.
It's not
Yeah, I mean,
Yeah, it's supposed to be dehydrated.
just not peanut butter. It's zero. Because this is 23 feet.
Alright, even doing like.
I went to the bathroom first.
Take out.
Oh, yeah, I just thought that would put it close.
Yeah, you don't
I had
want
like
to.
a couple of flowers.
okay. I wanna send you back for a moment to think about what they represented, that meaning the symbols here, and the conditional probability, because remember, we know that it equals this. But formulaically, this is Bayes' theorem, okay? Is that the probability of the outcome that you wish to predict conditioned on some sort of conditioning variable, right, that we all label as x's, that it equals, this form is not the likelihood function form, but it's the probability form that we will talk about initially, but then I'm gonna immediately move over to the priors times the likelihood, but this is just the probability, fundamental probability function, equation, formula. So what we have here are we have three probabilities, right? We have two unconditional probabilities, right? And we have one conditional probability. Okay, so what are these? Generally speaking, we consider this to be the base rate, and I also call that what? The priors. Okay, in the case of a point prediction, it is just a singular prior because there's only one value, it's a scalar. But in a continuum, they are considered to be the priors because there's lots of them that occur, and therefore they are put on a distribution or probability density function. Okay, so this probability either represents a point, and in this case, it does, it only represents a point estimate, a scalar, but in most instances, it represents a distribution. This, what's remaining, is what we consider the likelihood. Okay, but for the purposes of, instead of calling it the likelihood, I'm going to refer to it as two separate probabilities. One conditional and one unconditioned. Okay, now, as I said before, the probability of being diseased is 0.8, right? So therefore, the probability of not being diseased is 0.8, right? Okay. Now, probability of a positive test?
0.42.
0.42. Okay, so here the probability of a positive test, just the probability of a positive, is how many were here? Well, there's 18, right? Remember our n's, because we did everything in based on 100, makes it easier. There's 2, and there's 56. So Shane, I'm not agreeing and disagreeing with you. Rather than coming up with a number, we're going to work through the math, okay? Or math, arithmetic. It sounds a lot less, foreboding, right? You hear arithmetic and you're like, oh, okay, I'm cool with that. But math all of a sudden conjures up these weird ass symbols and stuff like that. But you already know. You look at these and you go, yeah, no problem. Carry under the curve. Talk about this. So how do we get this? Well, it's this and this, right? 18 plus 2 is 20, right? Over 18 plus 2 plus 24 plus 26, right? Okay, how do we get this? 24 plus 56, which is 80. Right? How do we get this? We get this plus this. Over 100. Is 100. 100 is easy. And this. Okay. The reason why I'm doing it explicitly is you may not always have 100. Sometimes you'll have a sample of 73. And you just got to calculate it this way. Okay. So I'm giving you all of the bits and pieces so you can calculate these on your own. Okay.
You have it in percentages, can you always just add them?
Yeah, because percentages are assumed. We assume that at some point you can normalize it to have 100. Okay. But here we've got these numbers. Wanted to show you how these numbers came about, right? This is an unconditional probability. Anytime we're calculating probabilities of a column or a row, whether it's about the outcome or the conditioning, the probabilities are calculated the same way, okay? So if I want to know the probability of this, it just goes across here. If I want to know the probability of this, it just goes across here. And as the denominator for any of these probabilities, it's the sum of all the cells. Make sense? The law of total probability. Okay, so our entire sampling space, bless you, is all 4 of these cells. Good? Okay. No student left behind. It's the same unfunded mandate that it always was. Okay, so you can see here that we now have probabilities. Now, let's look at conditioned probabilities. What is the probability that you would be positive given that you're this? Okay, so how do we do that? If unconditioned probabilities sample all of the cells, conditional probability would sample which cells? Remember what we did here? What we do is we're winnowing down the space when we condition. So when I conditioned before, I said, I only want to condition on, before I only wanted to condition on the positive tests, right? So I carved out just these, right? Okay. So if I don't carve out just these, but I carve out what? Just the reds, right? right? Because I'm conditioning on the reds. So if I condition only on the reds, out the blues, then I'm conditioning only on this, right? And so I get 18 out of 20, right? Now, how is that any different than this? Well, what's that probability? Right? Okay. This is the way we calculate these probabilities. They're either unconditioned or they're conditioned. They can be conditioned on any one of these. They can be conditioned on any column. But generally speaking, since this is the outcome, when we're talking about likelihoods, the outcome comes after. When we're talking about the posteriors, we condition on the antecedents. Okay? When we're talking about trying to calculate the outcome, as in the probability that the outcome would occur, we're conditioning on the antecedents. So we carve out based upon the antecedents. When we're talking about the likelihood, we are conditioning the likelihood on the outcome. This tells us what we're conditioning on. So it tells us where we slice up this. This method and this formula results in the same number. This is the traditional way of teaching Bayes' theorem. Okay? There are a lot of moving parts. That frequently with point estimates, people who calculate Bayes' theorem create, these are what are called truth tables. Okay? So truth tables, or hits and misses in signal detection, right? But we also look at this in disease detection. This is evaluating medical tests. A 2x2 matrix is a classic way of doing it, and it lends itself perfectly to calculating these probabilities. So these probabilities, what did we say? The probability of a positive test given that you're sick is this one. Okay, so by this, what we are doing is we are calculating Bayes' theorem according to probabilities. I will tell you that this will be the last time you'll ever want to do this because it is not useful. It is very hard to remember and it is prone to errors.
Sorry, you said truth tables are prone to errors?
Yeah. Calculating these probabilities, even though I just walked you through it all, I'm telling you, don't use that. The reason why I say don't use that is when Jim and I first started teaching Lecture Bayesian statistics, we had people do all of these things by hand. First semester was a train wreck. Not because of the students, because of us. We assumed that these types of calculations would be pretty easy, but it turns out that it's really complicated because students didn't always get here and the outcome here. They'd flip it and they get results that were different. They'd calculate these things on an n that wasn't 100, but think that these percentages somehow or another could be then translated back to frequencies of that odd number that we started with. Because we asked them proportionately how many of these patients are likely to test positive. Not just y hat, and for this is y asterisk hat, is for one prediction. Oops, sorry. Hat is typically I want to predict, and I want to predict any sort of outcome. That is, I want to predict one outcome. Okay. And when you start calculating with probabilities, all hell breaks loose. It becomes complicated and error prone. The method I prefer is I really prefer method of odds. I have my notes here. Okay. Sorry. I was going to do, the reason why I'm screwed up here is I was going to do the formula one first, and I decided, well, that's a stupid idea. Then I get more people dropping out of the class after the drop date. Okay, so the odds form. Odds form is pretty damn simple. You got to think in terms of odds. How many people are here relative to how many people are here? Okay. So for every one person here, how many of those one people could be over there? Okay, you see that? So for every one person here, there could be 4 people over here. Those are the odds. Okay? So what we would say, does that make sense? So what we would say is that prior odds I'm going to put a symbol here and I will explain it. Okay? Okay. That's my rendition of this fancy character that many people use about odds ratios, okay, or odds. When you see this, oftentimes you should just interpret this as this is the odds form. Here in the same text, they just do away with it. So all it serves is to remind you that these are odds, okay? But I'm going to start here just so that you know. And it is this kind of weird looking big ass graphical thing that I don't even know how to type. This odds, and these are called the priors. Because there's only one. Okay. We also have the likelihood. Okay. So the likelihood also comes in a similar format where it's going to be a number separated by a colon, another number. I want to tell you a little bit about likelihood because the odds that we start out with are called priors. They're subjective priors and they can be informed or uninformed. It could be a swag, right? A scientific wild ass guess. It could be a seat of the pants guess. Your grandmother could tell you. It can be anything, okay? There are no rules for whether your priors are informed or not. The more informed they are, the better you can defend your posteriors, and the more interpretable they are. But your priors are represented here in the odds form. The likelihood is the evidence. And if we have time today, I don't know whether we will, I'm going to talk about the relationship between the evidence, the priors, and the posterior. That is, the general form of Bayes' theorem is we have priors times evidence yields the posterior. Okay. This is the general form of Bayes' theorem. Okay. Once you learn this, it becomes really simple. It's just knowing what these pieces are. And the reason why I'm showing you this slowly in the odds form is when you see this, you're going to go, holy shit, that is easy. But until that time, it's still a black box. You already know it now. But we're going to talk about the odds form, and this is where you're going to become a mental calculator. You're going to be excellent at this stuff. The priors we've already talked about. What we really haven't talked about is evidence, or this likelihood thing. Now, I pointed it out in the probability formula, but I didn't make a whole big deal about it. But right now, I am. The priors are your best guess. They come from anywhere. It comes from data. Where the evidence comes from, though, is not always the way or the location or the method or the routine that the evidence comes from in frequentist statistics. Okay, so you're accustomed to, if you're graduate students, you're probably running around collecting data for your project, for your advisor's project, for your colleagues, for your classmates. You're running around and collecting data. And data collection is central to the frequentist notions of scientific inference. Okay, inferential testing in science, we collect a lot of data. So all that data collection that you're doing, you can either thank or you can curse the fathers. Say word. The fathers of there's probably a woman behind them and get all of that guaranteed. But the fathers of frequentist statistics, and in particular null hypothesis significance testing, Sir Ralph Fisher, he was knighted, and Jerzy Neyman and Egon Pearson. Those three, kind of separately, and then a lot of animosity together, created what we have today. But their model, and largely Fisher, is the model that you guys use today. Evidence in a Fisherian or in a traditional null hypothesis significance testing frequentist model, the evidence is from the data. The beauty of Bayesian statistics is that the evidence can come from anywhere. Now, that doesn't mean that you can tell your advisor to fuck off and you're not collecting any more data. You can't do that. Don't do that. Instead, you have to reconceptualize what evidence is. From a Bayesian perspective, evidence could be the single observation, one observation. Now we, here, in this example, we are asking for a hypothetical, a prediction of a single outcome that could be observed later on, given one piece of evidence. I didn't ask you to collect a lot of data. I just gave you the evidence. But you could still calculate the posterior probability because the evidence can come from anywhere. And it can be one single observation, or it can be a whole data set. That's why you still have to collect data. Sorry, guys. But by collecting data, you can then collect data at different levels to ask different questions. And to the extent that your data provides sufficient evidence to outweigh your prior expectations will lead to a change in your expectations after your study. Okay? Simple instance. If you think a person is nice and you walk up to them, you approach them and you start chatting with them, and they say one thing that's asinine, immediately your prior expectation of that nice person has changed. We are all Bayesians. We function this way. I don't see any of you running, well, I haven't yet, and I hope never to, seeing any of you running out in the middle of the street. Okay, why? Because you didn't have to collect any data. You just had to do this. What's the likelihood, the evidence, what would be the evidence necessary? Well, it just had to be one person hit by a car in the middle of the street to convince me never to do that. As Bayesians, you're constantly updating, okay? Now it's not necessarily true that we're not all formal Bayesians, but we think probabilistically and we think iteratively. Some of my students and I are interested in trust. Trust is an excellent example of this, right? Initially, if you're a trusting person, generally you're going to start with your priors being very high. That this person is very trustworthy. And then they provide you with a little bit of evidence, this person, this device, whatever the hell you're interested in, provides you with a little bit of evidence that maybe you can't rely upon them to deliver on what you want. And so therefore, it erodes trust, right? But oftentimes, it's not just like, it's, you screwed me over and you're now dead to me, right? That's the way we work. Now, that's a good example of where we're probably not very good Bayesians in that we're overreactive to certain things, right? We're much more averse to loss than we are to gains, right? This is why I say we are Bayesians, but we're probably not very good Bayesians. But that's okay. It's at least intuitively obvious that there is some updating where you have expectation, you gain some evidence, and then you have a new outlook in life. The cool thing about Bayesian, though, is you can take that same new outlook in life, provide some new evidence, and have a newer outlook in life. How do we do this? We do it intuitively. And we do it by looking at proportions. All right. So, if I say that my priors are 1 and 4, because how? Why? Why have I said my priors are 1 and 4? Where did I come up with that? Yeah, but where did I come up with that?
From the top.
Yeah. And this source, remember, is, yeah, I came up with it from this diagram. And this diagram is based upon overview of the literature, right? Something like that. But remember, it could be a scientific wild ass guess. Okay. Then I come up with a slightly different situation because it's conditional, right? Okay. Now, what are my odds here versus what is a likelihood? So I want to know the likelihood of, remember I showed you in the formula that the likelihood really is the this versus conditioned on that, right? It's a function of that. But the likelihood is a function of the people who are likely to be sick, right? If you're given that they're sick and then they test positive. So the likelihood has evidence that is consistent with everything that you know about in inferential testing. And what that is that. Okay. Look familiar? No? Yeah. So let's talk a little bit about this because this is important to connect all of this stuff together. And when you see it, you're gonna go, oh, that's it. Oh, okay. So the probability of the data given the hypothesis, as I said, this is the p-value. However, as scientists, we are really interested in something entirely different. Because what this tells us is it tells us what is the conditional probability that we would actually observe this data, given that the null hypothesis is true. That's why we want these teeny, teeny, tiny p-values, right? Because we want to falsify. This is statistical testing. But we, as scientists, have different views, right? First, when was the last time you were really interested in a null hypothesis? Never, I would hope. I would hope you'd be a little bit more creative. I think you're more interested in that. What's the probability that my theory is correct, given that I observed this data? Right? This is the posterior that we think about. But this is a likelihood. This is the evidence that is used to suggest that the posterior that we want is somehow or another defensible. Instead of defending the posterior, we defend the likelihood. Hence, you get the frequentist versus the Bayesians. You get the frequentist versus the subjectivists. And I'll tell you the reason why is that we don't lie to each other. We all care about the same shit. We do. We want science to progress. But because it's not progressing, what we do is we point to the obvious characteristics. The distinction between the likelihood and the posterior probability. As scientists, we care about posterior probability. As scientists who use frequentist models, we use the likelihood. Now, as I said before, this is the general form, the odds form, for the posterior probability. It just so happens to be the general form for the formula for Bayes' theorem and odds ratio form. This is the priors. This is the evidence. Priors by evidence. Yep.
Is the likelihood just that part, the p-value, or is it also the divided by probability of data?
In this form, it would be not the p-value, but it would be the odds. If you converted the p into odds, then it would fit this. Yep, this is only the odds form. Okay, important. Once you convert the probability into odds, right, then this formula works. Okay.
Can you have as many priors and evidence as you want?
Yes.
Have access to? It's not limited.
Excellent question. So Shane asked, can you have as many priors and as much evidence as you want? The answer is yes. Next week, when I expand this, I'm going to show you that we're going to take this really simple example and we're going to expand it to multiple outcomes, multiple priors, right? And having multiple priors is the first start, these are like baby steps, it's the first start in us envisioning from point estimates to a continuum. So yes, you can have multiple priors, and you can have, and along with the priors, you have to have evidence, likelihood form, odds form, that match those priors. But yes,
Is it always a pair, or does the prior need just at least one evidence?
it's going to need symmetry, and I'll show you more about that.
At G.
Oh, okay. So did I. Okay. So, so what do we get from this? There is, without question, there's 4 times more of these than there are these. And that's where we get that. And what we want is we just want that to be a placeholder in there. We know that those are our priors. But where does our evidence come from? The relative likelihood, okay, of positives, right, is what? The relative likelihood of us, now think about what the relative likelihood is. The relative likelihood, we are going to get, if you think about this, what proportion of the sick will test positive versus the proportion of the sick, unsick testing positive? Right?
So would that make it 3 to 1?
3 to 1.
That's 9 to 3. 90 to 330.
Yep. Okay. Do you see that?
What we did there was just adding the conditional probability, right?
What I did was I looked at,
Because we're only looking at the sample of sick people.
yeah. Oh, well, no.
The people testing positive.
Yes, sorry. You gotta think about when we're talking about the people who are testing positive, we want to know the proportion of them that are likely to be sick. So that's 3 to 1. Where the hell is this one? This one, right? There's 3 to 1. Now, remember, we did a really nice thing by having 100. You have to bear with me that not all of these problems start at 100. Pedagogically convenient. I don't want to kill you guys with 1,030.
So I get why the left side is 0.9. The right side is sample space. In other words, all the positives. Because in the probability one, it's the true positive over all positives.
Yep.
But in this one, it's the true positive over the false alarms.
Yeah, because remember, we can convert this odds ratio into probabilities, but they're not one and the same thing. Okay, the probabilities have to do with part over a whole, and ratios are part to part.
Oh, I see.
And I'm glad you asked that, because this is something I want to, it's my segue to just talk about where these numbers come from, to then say, what makes up a ratio in the sense that it is a ratio separated by this versus a proportion ratio that's separated by that, right?
So the whole is just both sides put together.
Yes. Yep.
Thank you.
So what we get, and you'll see that when we convert this to odds, you're going to find an annoying feature that in order to communicate with the rest of the world, you can't talk in odds. You have to talk in probabilities. Okay, so let's do that. Let's first do this. And since they're multiplicative, we multiply the same with the same location, and we get. Now you can see why I spent so much time going off in all these tangents. Because if I just did this, you'd be like, that's it? That's it. Done. But not so done. Because you can't talk to your grandmother in odds ratios unless she's a bookmaker. And if she is, well, she probably knows this probability stuff way better than you do, and you should be learning from her. But these odds are difficult to communicate. So generally speaking, we don't talk in odds. We talk in probabilities. So what we need to do is we need to turn. Now here's my segue. Sam's ahead of me. All you guys are ahead of me. All right. So in odds ratios here is a part to a part. Very important. Okay. And you'll see this as odds ratio, but in odds notation. So it would be one part to another part. But probabilities are often expressed as a part over the whole. Okay? Because of that, and that's the reason why, because we talk in terms of probability density functions, and we also talk a lot, and we're going to discuss this a lot in this class, about the law of total probability, especially when we have multiple events to estimate, and when we have multiple priors. We have multiple priors as in a distribution of priors, and we have a distribution of evidence. We keep reminding ourselves is that the denominator, every single time we're calculating a probability, that the denominator always has to be the whole. If it ain't the whole, there's problems. So if we have part to part, and we want to know this part to the whole, we just do right? Because there's 3 parts that we care about, and there are 7 parts in total. So 3 7s is the answer. Turns out it's the same answer that we had before. Twice. We're getting the same answers in 3 different ways, which is good. Now, all kidding aside about the probability formula, you may use the probability formula if you like truth tables and you find that they're useful, provided you don't make the errors, the common errors. You may use that. I find this odds formula super easy for point estimates. As long as you can make out what this is and this is. As soon as you can figure that out, and you're going to work through some examples. I've got great resources that I posted online. Avail yourself of them, okay? This example comes from, this example comes from one of those resources. It's this Bayes rule, a guided tutorial and all of that. It's really good. I wrote a bunch of notes from it, and I think it's top notch. You should go through it fully, okay? So what I've done is I have shown you Bayes' theorem step by step from frequency diagrams to the formula to then odds multiplication. This odds formula turns out to be pretty damn easy when you start thinking about priors and evidence. And how much does the evidence have to offset the priors in order for you to change your judgment? So we've already talked about that too. And we've talked a little bit about where our judgments lie on the continuum of 1.0 to 0, right? This is the cynic. The cynic has priors of 0. Everything sucks. Cynics are really hard to be around. Similarly, this is the true believer. Everything is great. They occasionally go there because you don't believe that everything is great. And then most of us who haven't the fucking foggiest idea what the hell's going on in the world, we all think a coin toss is that point of indecision or equipoise, and that in Bayesian statistics, we are interested in what do you think today? What kind of evidence is necessary for you to think differently than you do today? Not just conceptually, but probabilistically, okay? Bayes' theorem is about constantly updating us. The cool thing that I'm going to now extend a little bit of this is that the one thing that Bayes' theorem allows you to do is it allows you to carry over evidence from one instance to another. Frequentists, you cannot do that. Once you collect data and you test your p-value, your null hypothesis that you don't care about, don't worry, I have lots of pejorative things to say about null hypothesis significance testing, but I engage in it a lot. Like, oh, that's the forbidden fruit. We all use the tool. It's easy to beat up, but when you learn Bayesian, you'll learn how to use the tool better, but you'll also learn an alternative tool. So I do all of this stuff, and the problem in frequentists is once you run your p-value, you've collected your data, you run your analysis, you can't say, well, I just want to run it again, because you'll get the same damn results. What you can do is you can collect a little bit of data. You can have an initial guess. You collect a small bit of data, evidence, and you calculate a posterior. And that posterior becomes your new prior. And then you collect a little bit more data. And you calculate from that new evidence a new posterior. Lather, rinse, repeat. You can keep doing this. Now, at the smallest level, think of the evidence being one observation at a time, right? I mean, that would be brutal. You wouldn't want to calculate posteriors every single time. But you'd have a prior, then you make an observation, and you go, that's weird. And now your posterior is way over here. Because your prior may have been 0.5. And just a little bit of evidence will change your posterior to comply with the evidence. Oh, that's not me. It is me. Shut up. Yeah.
So in your lab, are you now exclusively trying to shift towards using fixed versus frequentists?
No. It's a tool. So Kevin, it would be like me building my deck, just a hammer. And everybody knows, deck building requires beer. So, no, and I think that's a real problem. That's what keeps everybody at arm's length from Bayesian. Because most of the Bayesians are nuts. They're crazy. They're like, they have this view of Bayesian and this view of frequentist models. And that's not me. I like the idea and the analogy of having a tool bag. So I have Bayesian tools, and I have frequentist tools. I have psychometric tools where there's no inferential testing, there's nothing about that. There's all sorts of tools that you can have. And if you use one at the exclusion of another, I think you kind of miss the scientific relevance of these tools. So yeah, we don't do that. And in fact, we don't do a whole lot of Bayesian stuff. We do it on the side, but we do it more subtly. But what you're going to learn is I'm going to tell you some of the tools. We have a little bit of time. I'm going to tell you some of the things that will become abundantly clearer to you in class. You'll understand what the hell would anybody bootstrap? Bootstrap is inherently a Bayesian procedure, but it's a Bayesian procedure applied to frequentist models. That's okay. The whole concept of random coefficients in linear mixed effects models, those are, while they're not resampled, those are in essence consistent with the idea of a distribution. Rather than a point estimate, it's a distribution of all parameters that may be suitable for individuals. That is much more akin to Bayesian than frequentists, and it's the reason why hardcore frequentists hate linear mixed effects models. They hate them. Now, as a scientist, I hate them too because nobody does anything. But there are a variety of other things. Missing data. The way we handle missing data with multiple imputation is inherently a Bayesian procedure. Okay? So there's lots of things that we use Bayesian procedures for that are nested behind the scenes. So it's good to learn this tool set along with the tool sets that you've already learned from 611, 612, regression, multivariate, whatever you've taken. Implement what you have and to expand your repertoire, right? Because I can swing a hammer and drink beer simultaneously. Not really, but they come in handy, you know? So that's what this class is going to be about. It's going to be about weaving this stuff in, but weaving it in afterwards. So at this point, we're only up to point estimates. And next week, what we're going to do is we're going to step forward with the idea of making the model slightly more complicated. Shane was he's trying to push the envelope. Most of you guys are, you know, asking good questions. What we're going to do is slowly work up our way from point estimate to distributions. Okay? And then in about 3 weeks, our first project will be due. Okay? So we're going to have 1 week where I'm going to force you to get together and really work on the project, and that will be the week before it's due. Okay? Because I know that everybody has, you're all busy, but this is the one time when I know it. So I know you can get together during class time, and the first instance and the first iteration, I want you to do it here. So September 22nd.
Sounds right.
Yeah.
It's 2 weeks from today.
Can't read my watch. I can't. What's the date today? The 8th. I need glasses. They're coming. 3 years. The 8th. 22nd. The 22nd, you will all convene here by team, and you will be working on your project together. That's not the terminus of your work together, but it's to ensure that everybody had the opportunity. We don't want to hear, I couldn't get away, and there was no way to communicate, and so doesn't answer email. No. You get one instance, and then we're going to work together on this, and then we'll reassemble the teams. Jake and I are going to create the teams, and we're going to create them sometime today, tomorrow morning. Right? And it's going to be based upon your responses to that little form. Okay? I hope you found it relatively entertaining. I did it late last night as I was falling asleep. I try to keep it entertaining, but mostly I need to know where your relative expertise lies. If you say that you don't have any expertise, that's okay. I would find an assignment. I'm just trying to match. I'm trying to spread the strengths out. So each team has an R person. Each team has a presentation person, a writer, a data person, a manager at a minimum. Okay. Sound good? All right, cool. Look on the website. I noticed that a lot of you look at the syllabus because for some reason, well, I have a lot of computers, I have a lot of monitors, and my syllabus just seems to stay up for most of the day, the last few days while I was working, and I see all of these anonymous things. You know, do you see that when you're logged in? It's hilarious. I see all of this like spread across. There was a time, I think there was about 12 of you on at the same time. So I was happy to see that. much happier to see that than see never. But stay up with the readings. Notice I didn't ask whether you read. Okay. Now you can just lie to yourself. Continue reading, but also read some of the stuff, the optional stuff that I post, because I'm posting stuff that, again, just kind of pulls some of this together. This orbital.com is this website that this guy created. He wrote this fantastic primer on Bayes' theorem that we used years and years ago, and he rewrote it into this nice interactive method. And he's stolen stuff from Andrew Gelman. We've all stolen stuff from Andrew Gelman because he's awesome. But I am trying to distill what this guy is doing so that we can move on. Okay, so it's my story, but follow what he does because he offers a bunch of examples. If you want some problems to do, some people like that, like do little word problems and stuff like that. Fred Mosteller has a book that is now, I think, freely available. Of course, nowadays everything's freely available somehow or another. You know what I mean? You know that there's stuff in PDF. Just look for Mosteller probability problems PDF, and it will show up. I'm not advocating that you search for stolen property, students, and you're dirt poor. So, avail yourself of all resources possible. Fred Mosteller's 50 Challenging Problems in Probability. Great thing to start with. The problems get so hard that I suggest you stop, because you just end up pulling your hair out, getting really frustrated. But you can solve all the problems with these basic tools. Basic probability theory, he not only has the solutions, but he walks through the whole logic and where people go wrong. I will post all of these resources. Obviously, I can't post Mosteller's book. Fred's, if not, it's really old. But I don't think he'd be really appreciative, or his family, that I was posting his copyrighted material online. But do search for that. There are a bunch of examples in the textbooks. Did anybody email Aziz about Barry? Yeah, good. If you get a chance, you should read Barry's good stuff. It's $150 if you're married to an incredibly wealthy person. Sponge off of that person and get the $150 book. But if you're not, yeah.
There's copies on Amazon really cheap, like used ones for $8 or something.
Really?
Old edition or something.
No, it doesn't matter. He didn't update it. He did not update the book. I emailed him and his son, and they both said that they were too busy to update the book. It doesn't pay, like you publish a book and you get $3 royalties every year. So, but that Barry book, what is it? Understanding Bayesian Statistics?
Bayesian perspective.
Bayesian Statistics from Bayesian perspective. It is an outstanding book. It is the single best introductory book on Bayesian statistics.
And start at chapter 5 too. The first 4 chapters are like means and like really basic stuff.
Yeah, like univariate statistics that you would hope you know, not you. But chapter 5 onward, it's good stuff. And we do have the answers to all the problems.
They weren't as satisfactory. I'm gonna give you that. I have the answer key, that book. We can
No, you have the answer key from the back of the book.
Right.
No, we have the answer key from the whole book.
Okay.
I just have to email somebody and find out what the hell it is.
Okay.
Yeah. Cool. But we do have the answer to the book. So if you're interested in doing that, and most of us have worked through the entire book and done the R application because Barry did it all in on a 3.5 inch disc, floppy disk.
Speaking of R,
Mhm.
those of us who came to the class not knowing R,
Yes.
where on the spectrum of like not knowing shit about R and knowing R should we be right now?
You know, that's a tough question. Where should you be? I don't like should. Should is very Catholic.
What effort?
Where would I like it?
Recommend, where would you recommend that we be?
Yeah, where would I recommend? Okay, where I recommend, I think it would be wise if you were able to in data and maybe do some quick summaries with that. Just do a lot of the variables, so low level. And the reason for this is you guys are going to learn. Sorry about sitting down. My back is killing me. You're going to learn more from one another working in groups. Now, our aficionados, you're not to do all of the shit in R. Okay, you want to like give people who are struggling with R a little bit to do, so that they can learn along the way. The R experts are really there to make sure that R is functioning the way you want it to. Okay, somebody is going to be responsible for kind of making decisions about the data analysis, and you don't need to know R for that initially. Once this first iteration goes, somebody has to step up and be the new R expert. So that'll be for project 2. So now, expert doesn't mean expert. It just means that you need to know enough about R that when it gives you this warning message, if you can't interpret it, you can go to one of the local experts and say, hey, that's this. Or if you guys collectively can't figure it out, then you come to Jake and me and say, what the hell's going on here? So where ought you be for R? Pretty basic.
There's just this anxiety, it's like,
Yeah.
don't know it, don't know what I should know.
Yeah.
So I just
You
want to
know
make
where
sure
to go,
that-
yeah. But you have, so everybody has Swirl. You can go through Swirl. It's kind of a fairly quick intro. I went through it when it first came out, so it's been a while ago. Maybe a year or so, 6 months ago, just because I was curious as to what it did. It's pretty quick. So if you just spend like 15 minutes a day just pushing the ball forward, you'll find that much better than sitting down and doing 4 hours on it. See what purges from your brain after those 4 hours. Yeah, pretty much everything. They're like, R? What is R? So, yeah, and you'll get a feel for where you need to be when you start interacting with your teammates. Okay? All right. Other questions? So far, so good? Too slow? Too fast?
I just want to double check. So we aren't actually supposed to be starting to work with our groups until we meet in that class that day? Or
No, beforehand, when you figure out who you're.
Yeah, well, once we figure it out, and then we're beginning to work on it before
Yep,
class.
full steam ahead. Yep. Yeah, so once Jake and I create the groups, we send out the group assignments. You guys will have each other's email addresses. What I do with my students is I meet via Google Hangout. It's really easy. You don't have to be in the same physical location. You can all meet. You can have an agreed upon time. Hangout it works. You don't need to install a bunch of software and all that. If you don't have a camera, you can just use your microphone. So the camera's not effective. That way you can all say your jammies and chill out at home and have a glass of wine. But you should do it so that the more times that you meet and the more you discuss it and manage it, that you get a clear idea right away about what you want to do, the responsibilities. Okay? And there'll be one person that will be like, the ass kicker. That's the person I say, what was the answer choice? I run my household
Like a
like
German something.
with German
With
efficiency.
German.
Yeah. Did you see the form?
Yes, I pulled it out.
Did you? Yes. Did you? So did you answer? Yeah. Do you run your household with German efficiency?
I read about that one. Actually, no, I don't even know what it means. I don't know.
You know what? So I'll email my friend Oliver and I'll say, Oliver, how do I make this joke? He'll say, you can't. We don't joke.
In all honesty, maybe the opposite of American inefficiency.
Oh, yeah. Yeah, like my household.
Just the opposite.
Yeah, the opposite. Perfectly run household. Is yours not like this?
So is it likely that we'll be meeting in a different room next week?
Yeah.
Or are we like right on the
Probability is, I would give it 0.4. Mike is very resourceful, but the university has like this, it's the law of disappearing resources. Where, they'll tell you that they've got a faculty lounge. They'll say, after 1 week, we've decided that not